Video 2 for lesson 10.3 on chords. So now we have another theorem, theorem 10.5 and its converse, about chords and being equidistant from the centers, right? So the theorem says if chords are equidistant from the center of a circle or the centers of congruence circles, then they are congruent. So the idea here is the fact that if a chord, right, has the same perpendicular distance to the center as another chord, then those two chords are congruent. Now again, it's hard to mark that AB is congruent to CD, but that's the end result here. Vice versa, right? If we know that AB and CD are congruent, then we know that they are the same distance away from the center. So we know that these are congruent. We also have to know that these are right angles, right? Because that represents the distance from the chord to the center. So you can easily see that, and I'll do it right here, that if we connect the center to one of these endpoints, we create a right triangle, and you can see the application of right triangles with this theorem. Now I do have a Savas little thing to show you, so let me get Savas loaded up. Alright, so it says drag points A and B to change the length of the chords, drag point F to rotate the chord around point S. Alright, so let's see what this does. Okay, just thinking. Alright, so again, I think it says to drag points A and B to change the length. So if I drag A, notice I change the length of both chords, but notice the distance stays the same. If I take F and I rotate that, again, you can see that as long as the chord stays the same, and this is a perpendicular distance, these two distances are the same. Okay. All right, so let's go ahead and create a proof of this. This is kind of a lengthier proof, so I apologize for that. We are going to use what's called a flow proof. So we did a paragraph proof in the first video. Now we're going to do what's called a flow proof. Flow proof uses arrows. It's more organized. You're going to see that this is going to be pretty hectic. We're going to try to go. I don't have a lot of space. I'm going to try to go left to right. I might have to erase, which I apologize, which is terrible. But we'll see what I can do. Okay. So in this proof, we're going to prove theorem 10.5, which states that if two chords are equidistant from the center, then they are congruent. So in this problem, we're given that circle P has lengths chord AB perpendicular to PE, CD perpendicular to PF, and we know that P to E is congruent to P to F. So we know that this is congruent to this. And we're going to prove that AB is congruent to CD. All right, so we have two givens, right? We're going to start with the perpendicular givens. We're going to kind of put them together. So we know that segment AB is perpendicular to segment PE, and we know that segment CD is perpendicular to PF. And again, we write the statement and we put the reason underneath it. That's given. Okay. So what does that mean? Well, that means we have a couple right angles, right? We have 4 to be exact, right? Because we have the 2 that are marked and then these 2 as well. So we know that angles APE, BPE, CPF, and angle DPF, right? All those right angles are right angles. Are right angles. And that's by the definition of being perpendicular. Okay. So we're going to pause there for a second. Next, let's go with this. The PE is congruent to PF. That's a P, right? This is also given to us. Okay. So what we have here, right, is we have a situation to create triangles. And because we mentioned all 4 right angles, we're going to create all 4 right triangles like so. I'll do it in blue. So by doing D to P, D to C, A to P. Okay, so all of those are radii of the circle because they go from the center. So all of those are congruent. So I'll use double dashes. So that's a completely separate idea, which I'm going to go right down here. And again, this might be tough to squeeze. I apologize. So I'm going to do it in the color. So we're going to say that AP is congruent to B, P is congruent to C, P is congruent to D, P, and that's because all radii are congruent, right? It's a triangle, or it's a circle. The radius is the constant. That's what makes it a circle. So all radii are congruent. So now in this picture, because we have right angles, we have right triangles. And those radii are the hypotenuses of the right triangles. The segments PE and PF are a pair of legs. We can use HL to prove these triangles congruent. Now we have to mention that they are right triangles. So because they have right angles, we can say that triangle, and I'll use the same namings, APE, BPE, CPF, and triangle DPF are right triangles. And that's just by the definition of a right triangle. And now, because we have right triangles, let me do it in green. Because we have right triangles, because we have a congruent pair of legs, and because we have congruent hypotenuses, if we bring all of these ideas together, and this is what I like about flow proofs, is that you can be kind of creative. If we bring all those together, we can say that those four triangles are congruent to each other. So triangle APE is congruent to triangle BPE, is congruent to triangle CPF, is congruent to triangle DPF, and that's by HL congruence. So now the ending here is a little bit too much, in terms of like what they make you do, very formal. So because of that, right, we know that all the corresponding parts are congruent. We now know that AE, BE, CF, and DF are congruent to each other, which are going to help make these chords, right? So I'm going to write this down and then erase. I apologize. So we know that AE is congruent to BE, is congruent to C, F is congruent to D, F, and that's by CP, CTC. Okay, so from there I'm going to draw an arrow and I'm going to erase, right? Because we know those lengths are, or those segments are congruent, right? We now know that those lengths are equal. So now we can say that the length of AE equals the length of BE equals the length of CF equals the length of DF. And that is by the definition of congruence. You could say congruent segments, but it's fine. Okay, so now I have to bring in a different idea, okay? Because we have these four lengths, notice that AE and BE together make AB. So we have to do some segment addition. So this is going to come out of left field, right? So find a spot in your paper to kind of put it near that statement, but a little bit away from it. And we're going to say that, so AB is equal to AE plus EB, or BE. I'll do BE. And we know that CD is congruent to CF plus DF. Or not congruent to, equal to CF plus DF. And that's the segment addition postulate. So now if we bring these two ideas together, right, and we do some substitution, right, we can substitute AE in place of BE. So we can take out BE and put AE in its place. We can also, in the second one, we can take out DF and put CF in its place because they're all equal. And we'll get these two equations. So AB equals, so AE and AE would be 2 AEs. CD equals CF and CF, which is 2 CFs. We did that by substitution. And again, we know that AE and CF are congruent because it says it right here, they're equal. So we know that these two are congruent. If we did some substitution, we could then say that AB is equal to CD. So AB is going to be equal to CD through some substitution. Again, it might be a couple steps, but we're going to try to shorten it up. And if these two segments have the same length, then they are congruent by the definition of congruence, or congruent segments. And there you go.